Good morning everyone. I'm Shaaktam and we'll be taking 5 integral questions from the probability and combinatorics chapter, which are likely to appear in some form or the other in repeated examinations such as PRMO, IOQM, etc. So the first question we'll be discussing itself is a very interesting one. It's a round table question, round table conference question. What are the details mentioned of this question? Essentially, there are 5 men and 5 women, and there are 6 seats on a certain round table. There are 6 seats. Now, we have to figure out the total number of ways in which we can occupy these 6 seats in such a manner that no 2 women are together. No 2 women are together. So we want to figure out an arrangement in which there are 6 seats to be occupied in a round table conference by 5 men and 5 women in such a way that no 2 women are together. Now let us examine the number of ways in the starting how you can occupy. You can keep 5 women, 1 man, 4 women, 2 men, 3 women, 3 men, 2 women, 4 men, and 1 woman, 5. Now, in these initial 2 cases, you can see that it is guaranteed that 2 women will be sitting together because they are significantly outnumbering the number of males. So these 2 are not possible. We'll have to look at all these 3 cases individually to figure out the total number of ways in which no 2 women are together. So let us go case wise. Let us start with the first case, 1 woman, 5 men. Let's replace it to 5 men and 1 woman. Right? So this is our case 1. You can rewrite it because the space in this question is essentially required. Right? Okay. We need 5 men and 1 woman to occupy 6 seats. Now, initially the number of men and women we have is 5 men and 5. So to pick 5 men out of 5 men, now obviously there's only one way, but for our understanding we'll write this as 5C5. And how many ways can you get 5 men out of 5 men? Similarly for women, in how many ways you can take 1 woman from 5 women will be 5C1. Why are we multiplying and why will be consecutively multiplying? Because only after all these events are completed can our job be done. It is not an either or situation where you can add and even if one of them is done, it will be completed. You require all these events to be completed for this certain job or event to be completed. Right. So 5C5 is the number of ways in which you can pull out 5 men, and 5C1 is the number of ways in which you can pull out 1 woman. Okay. Now, we need to understand in how many ways can you seat 5 men in a circular arrangement. The formula actually for seating 5 men will be 5 minus 1 whole factorial. But why is this the formula? Let us consider, for our understanding, 4 men A, B, C and D in 2 cases. Right? In one case, they are being arranged in a circle where let's say the initial order is A, B, C, D, and a second arrangement where they are in a line. So you have A, B, C and D. Now what do we do in this situation is, let us move one place to the left or to the right. Okay? So here we have A, B, C, D. Let us change this to, for example, let's move D up here. We get D, A, B, C. Right? We can again shift it to at C, D, A, B. And then we can again get B, B on top, C here, B here, C here, D here and A here. And then we'll again get A on top. Right? Now if you look at this case, if we move one space, then D will come here to make the order DABC. Then C will be here, C will come here to make the order it will be DABC. So then the order becomes CDAB. After that, when we will move, we'll get BCDA, and then we'll be back to ABC. This is the initial order. Now, what I want you guys to look at this. We get 4 cases, right, in a similar fashion. We also get DABC, CDAB, and BCDA, and then back to ABCD. However, the actual order in all the cases for a circular arrangement is ABCD only. Look, the starting case is obviously ABCD. You again have ABCD. You've just shifted them. Yes, we are acknowledging your shift, but at the same time, the order is the same. However, when you're considering a line, the order is changing. It was ABCD. Now it is DABC. So DABC is a completely new order altogether, and since this is not a circle, DABC is not the same as ABC. So in this case of 4, what we get to see is that so you got 4 arrangements for a line for the same order, initial order ABCD, but this accounts for only one. At the end of the day, there is only one circular arrangement we accounted for 4 linear arrangements. So one circular will be equal to 4 linear arrangements. Right. Now similarly, if you arrange n things, right, then n circular arrangements will be equal to n linear arrangements. What does this mean? It means circularly arranging n things will be equal to so you have n number of things to consider. One arrangement of one circular arrangement of n things will be equal to n linear arrangements of n things. Now, in how many ways can you linearly arrange n things? Means that if you have a line, how many ways can you arrange n things? It's simple. We know that is going to be n factorial. Why will be n factorial? This space can be occupied by n. Now there are n minus 1, n minus 1, n minus 1, n minus 2, n minus 3. So there are n factorial arrangements in total. N factorial linear arrangements, right? But we know that every one circular arrangement, one circular will be n linear, right? So if we use unitary method, then 1 by n circular arrangements will be one linear arrangement, and therefore if we incorporate n factorial, which will be the total number of ways in which you can arrange n things on a line, then you will get n factorial divided by n circular arrangements, which will essentially be equal to n minus 1 whole factorial. Right? This is what we're going to get, because we know that one circular arrangement will be equal to n linear arrangements. By unitary method, we came back to 1 by n circular arrangement will be equal to 1 linear arrangements. So n factorial linear arrangement will be equal to n factorial by n circular arrangements, which is n minus 1 factorial. Therefore, since we are considering a circle in this question where you have to arrange 5 people, you will get 5 minus 1 whole factorial. Okay. So till now, what have we covered in this question is 5C5, how many ways can you select 5 men? 5C1, the way of selecting 1 woman, and 5 minus 1 whole factorial, the number of circular arrangements for 5 men. Right. Now, you have to accommodate 1 woman. So let us actually take a circle where you've already accommodated 5 men and you're finding a 1 seat for a woman. Right. So you have 1, 2, 3, 4 and 5. These are all men. Now, a woman can occupy any place in between, right? So a woman will have 1, 2, 3, 4 and 5 seats. And since there's only 1 woman for 5 seats, we will multiply 5C1. What does this 5C1 represent? This 5C1 represents the number of ways in which 1 woman can occupy 5 seats. Why are there 5 seats? Because there are 5 men seated already, right? Into 1 factorial. 1 factorial by, now in this case I only considering 1 woman. But when we consider, for example, 4 men and 2 women, even after the arrangements, those women can swap with each other. So you have to account for those arrangements as well in tandem with what we have already considered, right? So that will be 1 factorial. Now, this is one part. Let's do the calculating part. 5c5 will obviously be 1. 5c1 will be 5. 5 factorial will be 5 minus 1 for 4 factorial. Again 5 into 1 factorial. Right? So we'll get 5 into 5. 4 factorial can be simplified as 24, of course. 25 into 24 is 600 ways. Now 600 ways is one case. We are accommodating 5 men and 1 woman. Now let us look at the second case. What are we going to do in the second case? So we have already done one case. 5 men, 1 woman is 600. Now we look at 4 men and 2 women. We'll now move on the similar part. Now you're selecting 4 men out of 5 men, which can be done 5c4 ways. Last time we did 5c5 because we're selecting 5 men out of 5 men. Now we're selecting 4 men, so it will be 5c4. Similarly, there are 5 women, of which you're selecting 2, so 5c2. Now, using the circular arrangement logic, in how many ways can the men accommodate themselves in the circle? The men can accommodate themselves in the 4 minus 1 whole factorial number of ways. Why? Because n minus 1 whole factorial for circular arrangements of n things. Now, we'll move how we did last time. 4 men have already occupied their seats. There's space for 4. There are 4 spaces for them to occupy. 1, 2, 3, 4. And there are 2 to be seated. So this will be 4c2. So we multiply it by 4c2 and into 2 factorial y, because there are 4c2 ways for them to occupy, but these women can interchange their seats with each other. If one A is sitting here and one B is sitting here, B can sit and A sitting here, we'll also have to account for that change. Right. 5c4, you're selecting 4 men. 5c2, you're selecting 2 women. 4 minus 1 factorial, the number of ways in which you can circularly arrange 4 men. 4c2, number of seats, C, the number of women that you're occupying, and 2 factorial that they can interchange with each other. Okay, so 5c4 is going to be 5. 5c2 will be 5 factorial by 2 factorial, 3 factorial. Then again multiply with 3 factorial. 4c2 will be 4 factorial by 2 factorial, 2 factorial. Again into 2 factorial. You can see you can actually cancel, right? So then you're getting 5 into 5 factorial is of course 120 divided by 2. Again this can also be cancelled. 4 factorial is also 24 by 2. So at the end of this you're getting 5 into 24. Sorry, 5 into 60 into 12. Okay, 5 into 60 into 12, 300 into 12, 3600 ways for 4 men and 2 women. So 4 men and 2 women, 3600 ways. And finally, we will now look at the equal number of cases where now you have 3 men and 3 women. Now 5c3 was selecting men, 5c3 again selecting women. 3 minus 1 whole factorial. In how many circular arrangements are there for arranging 3 men? Now, can use our faculties, right? We again have just 3 spaces for women and 3 women to occupy. So that will be 3c3 into 3 factorial by 3 factorial because they get interchange, right? So again you will get 5 factorial by 3 factorial, 2 factorial whole squared. So this is repeated into 2 factorial, which is 2. 3c3 will be 3 factorial, which will be 1 into 3 factorial, which will be 6, right? So 5 factorial will be 120 by 6 into 2 whole squared into 2 into 6 to be 12 over that side. So 120 by 12 will be 10, 100, 112 will be 1200 ways. 1200 ways, right? Now our event, our job where no 2 women are sitting together is going to be completed in either of these cases. Now look at the usage of multiplication and addition. When I was considering one case, for example 4 men and 2 women, then that scenario is only completed after I multiply and all the jobs are done. But if we consider these three events as completely separate events from each other, either of these cases are good enough for me. Good enough in the sense, if any of these three are completed, my job is sorted. So that's why I will add them all together. It's going to give me 5400. So you have 5400 ways. So in conclusion, if you have 6 seats, 5 men and 5 women, there are 5400 ways to accommodate these people such that no 2 women sit together. And very intriguingly, the fact that the number of men and women are equal, this will also, 5400 will also be the number of ways so that no 2 men are sitting together. Right? Because it's exactly, you'll move the exact same way, just we'll switch M and W. Right? Now we'll move to the second question, which is injustice in toys. Okay, what does this question read? This question reads that there are n kids and n toys to distribute between these 2 kids. We need the number of ways such that one kid, one unfortunate child, gets 0 toys. A very catharsistic question, because we are finding pleasure in giving this child no toy. Nevertheless, let us look at what we need to do. Now, since there's only one child getting no toy, we require one child to get no toy, one child to get 2 toys, and n minus 2 children to get n minus 2 toys. Okay, let's complete this event first. In how many ways can you select a child out of n children? One child. It would be NC1. NC1 will be n factorial by 1 factorial into n minus 1 factorial. So this will give us n. There are n ways to select one child out of n. Now, in how many ways can you select one child out of n minus 1? Because now I've already selected the child who is not getting toy. N minus 1 C1, which will also be n minus 1. It will be n minus 1 instead of n. Now 2 toys. There are n toys. Which 2 toys out of the n toys are the ones that you want to give to this specific child? There will be NC2 ways to find out. Right? And if there are n minus 2 toys to distribute between n minus 2 children, then there will be n minus 2 whole factorial ways to do so. Now all is left is to multiply. So n into n minus 1 into nc2 into n minus 2 whole factorial. We can rewrite this as nc2 into n minus 1 into n minus 2 whole factorial. Now, leave nc2 aside and look at the equation. We can substitute n into n minus 1 into n minus 2 whole factorial as n factorial. Why so? Because n factorial will be n into n minus 1 into n minus 2 into n minus 3. N into n minus 1 is already completed and n minus 2 factorial is the remaining. So at the end of this, you'll get n factorial into nc2 ways. Okay, and look at the question again. What was it? There were n kids with n toys. You have to find a way in which the number of ways in which one kid gets 0 toys. So you first need to find out the one kid getting 0 toys. There are n ways to select this child. Then there are n minus 1 ways to select that one child who will get 2 toys. N minus 1 C1. Which 2 toys will you accord to this child? There are NC2 ways. You are selecting 2 toys out of n. And there are n minus 2 children left for n minus 2 toys to distribute. N minus 2 factorial ways. And then at the end, when you will multiply after all the calculation and numerical work, you will get n factorial into nc2 ways in which you can distribute n toys within among n children such that one child will get no toy. Now the third question for today is revolving around an inequation. Inequation. What do we have to consider in this question? So we have, it's actually an equation, but we are writing in an oxymoronic way because it's an inequation and we can have multiple solutions for this. Right? The inequation. So we need to find the values of x, y and z, where x plus y plus z equals 20, where there are 2 scenarios, 2 conditions. x is not equal to y is not equal to z, and x, y, z are all members of positive integers. Positive integers, or you can obviously write as n instead of natural numbers. Right? Now let us utilize this condition first. Let us say that y equals x plus alpha, right? And z equals y plus beta. Right? Now, if we rewrite this equation, then we can write it as x plus alpha, and y can be again written as x plus alpha, so plus x plus alpha plus beta equals 20. So 3x plus 2 alpha plus beta was 20. Right? Now, since they are positive integers, let us take cases. Let's say x equals 1. You get 2 alpha plus beta equals 17. And alpha can take, and this can have 8 values. Right? Because till this is 16, beta will have 1. So it will be 1 and then 15. If you reduce, you finally get 8 ways. Right? Similarly, when x is 2, you get 2 alpha plus beta equals 14. It will be 6 ways. So this will be the number just close to it. Will require till 12. Then when it's 3, you get 11. 11 means 5. And x is equal to 4. You get 2 alpha plus beta equals 8. And middle 3. Then you get till 5. 2 alpha plus beta is 5. Is 5 and 15. Now you can do 2. And after that you cannot do. Okay? Now, you get 8, 6, 14. And at the end we get 24 ways. For x equal to 1, x equal to 2, x equal to 3, x equal to 4, and x equal to 5. So we get 24 ways. Is our answer complete? What have we not realized? If you look at it, x, alpha and beta were concepts we introduced. Now, for example, let's say you take this one solution of this, where you get, let's say 1, 8, 1. Right? Because x equal 1, the 3x and 16, 120. Okay. Now, since these are introduced by us, we can actually interchange them in 3 factorial ways. In this they are common. But otherwise, when we'll get the different values by adding alpha and beta, there will be 3 factorial ways which we'll have to multiply. So this will be 144. There will be 144 ways in which x plus y plus z equals 20, and they are all distinct, with all these numbers being a member of positive integral set or a set of natural numbers. Okay? Now let's look at the next question. For our next question, we have a 15-sided regular polygon. 15-sided regular polygon. We have to find the number of ways, or not number of ways, the number of triangles you can make, such that no side coincides with side of polygon. No side coincides with that of polygon. Polygon, right? Now, if you look at it, essentially, the total number of triangles you can make from the vertex of an n-gon. N-gon means an n-sided polygon. From vertices of n-gon will be equal to the triangles with one side common, triangles with 2 common, and triangles with no common. Triangles with no common. Now, total triangles you can make from the vertices are basically, it's in a way asking you for selecting 3 random vertices out of n. which is NC3. Right? Now, these are two things you have to figure out logically. Right? You have to figure out how many triangles you can make with one side common from an n-gon, and triangle you can make from a two sides common. And then this is what you want to find. And then we replace 15 and then our job is over. Right? So let us look at triangles with two sides common first, because this is an easier job to do. Let's take an octagon into consideration. Right? Now, you need two sides common. Let's say you're taking this side and this side. 1, 2 common. Right? For these two sides, you can make one triangle. And similarly, you took these two, now you take these two. So at the end, how much will you get? You get 1, 2, now in this case you get 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8 and 8, 1. Similarly, if you take an n-gon, you get 1, 2, 2, 3, 3, 4 all the way up to n1. So therefore there are n number of triangles you can make with two sides common with the side of the polygon. Right? This is all logical. And we also showed this with the octagon. Excuse me. Now let's take another octagon to do our second job, which is trying to find the number of triangles you can make with one side common. Now follow me on this one. Let's say I took this top side. Which vertices can I not take? I cannot take this vertex to make a triangle because this will make it two sides common. Neither can I take this vertex to make it because this will also make it two sides common. So I am left with how many? Now, I am left with this vertex. I am left with this vertex 2, this vertex 3 and this vertex 4. Right? So we made 4 triangles and this can be repeated with all the sides. So, in this case, we saw that there were 8 vertices. We get 8 minus 4 triangles for each vertex, and we can repeat this 8 times for 8 sides. Now, if you logically look at it in another way, let's say this is not an octagon. This is some kind of regular polygon. Regular polygon, but I have not drawn regularly. Now, if you take two sides, the only two vertices other than so there are n vertices in this, you can't consider 1, 2, 3 and 4, right? So there are n minus 4 vertices for you to consider. So you can make with this vertex, this vertex, this vertex. There are n vertices of which you can't consider 4. Because 2 are the ones making the actual side with one side common, and the 2 other ones which will make it a two side common. So it will not be in our case. And this you will again repeat. So you can make n minus 4 triangles with each side, and then you will multiply to make it n into n minus 4. It will be n into n minus 4. And this is what we have to find, the triangle with no side common. Right? Now this is very important because it's not just about probability, it's about geometry and logic about connecting polygons to probability. Right? So this is a 15 side polygon. Let's replace 15C3 plus 15 times 11, 165 plus 15 plus let's say x, there are the number of triangles with no sides common, what we want to find. 15C3 will be equal to 15 factorial by 3 factorial, 12 factorial, and this will be equal to 165 plus 15, 180 plus x. Now, we will get 15 into 14 into 13 whole by 6 equals 180 plus x. 180 plus x. If you remove 6 over here with 15 for example, you get 5, 2, 5, 7, 5, 7, 35, 35, 13. You will get 455 equals 180 plus x, and then x equals 275 triangles. So then we have come to a conclusion that for a 15-sided regular polygon, the number of triangles you can make with no side common with the side of the polygon is 275. Now let us come to our final question for today. Bag of bombs. in this question, you have n white and n red balls in a bag. And what we are doing is we are pulling out 2 without replacement every time, right? So the probability, we need to find the probability that every pair we pull out has 1 white and 1 red. The probability in this is not the number of ways. We have to find the total events and then find the favorable outcomes. So let's find the total events, our sample space as we can call it. Now, the total number of balls you have to consider are 2n. And then you're pulling out 2. When you have pulled out 2 and you take them out, you have 2n minus 2 left. And this will repeat until our n is already met. 2n minus 4 dot dot dot. Now 2n, we get 2n whole factorial by 2 factorial into 2n minus 2 whole factorial, but this will also be 2n minus 2 whole factorial by 2 factorial into 2n minus 4 whole factorial, and this will be 2n minus 4 whole factorial to 2 factorial into 2n minus 6 factorial. What you can observe over here is we can cancel one part of the denominator with the numerator, and this will continue. You will cancel this with the next one, etc., etc. At the end of it, you will get 2n whole factorial by 2 factorial whole raised to n. Why 2 factorial whole raised to n? Because 2 factorial has been repeated n times. How do we know n times? Because you have 2n and you are pulling it out 2 at a time. That will be n ways. So the total sample space we have is 2n whole factorial divided by 2 factorial whole raised to n. Now, we need to find our favorable outcomes. So let us rewrite over here that our total is 2n factorial by 2 factorial whole raised to n. Okay. Now we need to find a favorable outcome. So that in one pair, you get 1 white and 1 red. So let us look at it pair by pair, and in every pair, the ball we are pulling out in each, right? So a favorable outcome. Let's look at the first pair. You want 1 white. Now there are n white balls, out of which you need 1. So nc1. Similarly, n red ball, out of which you're pulling 1 red ball. So nc1. Because these are favorable. Similarly, after this you're now left with n minus 1 c1 to n minus 1 c1. And then to continue. Right. So we can actually write this down as n c1 into n minus 1 c1 dot 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 whole squared. Now let's look at this as well. This will be n factorial by 1 whole factorial, n minus 1 whole factorial. It will be n minus 1 whole factorial by 1 factorial raised to n minus 2 factorial. Now if we ignore the square part and then this dot 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 will continue, this can again get cancelled with the numerator and the denominator. 1 factorial will be 1 only, and so 1 factorial will be continued how many times? We are pulling it out, so it will be counted n times. The 1 factorial will remain 1. What will still be remaining is n factorial on top. That will be whole square, so n factorial whole square. Therefore, our probability for this event to take place will be favorable by total. Will be n factorial whole square by 2n whole factorial, and this will come up into 2 factorial whole raised to n. So this will be our probability for the event to occur, where every pair we are pulling out of a bag of balls where we have n white and n red balls. Every pair has 1 white and 1 red ball. That is it for today. Thank you very much.